Hello guys, welcome to the channel. Let's see mm, moving target for a moving platform. So moving target indicator from a moving platform, they are called actually airborne moving target indicators. So you can see that there are some bulb type structures on helicopters and some aeroplanes, a flat disc, and you can see these radars on navy ships and all. And any ship, every ship will have some radar system. Yeah, like big ships and all, they have a radar system on it. So basically the platform is moving. So when as actually in previous session we have seen that only the radar is fixed and the target is moving. Here the both are moving. So uh, since the radar is itself moving, it can also cause the clutter, right? So as I told already, clutter, it is due to caused by the moving body, caused by the moving bodies. So by which, as I said already, mm, so if you take a pulse, okay, if you take the pulse PRF, it is like this, and there will be clutters right in between. So there will be clutters. So what happens if it when the radar is also moving, what happens, this width will be getting increased. So actually it should be zero. To make it zero, we have used we have done previously had in two methods as Doppler filters and all, right? And hmm, basically now it's not like that, it's actually radar also moving. So to eliminate that, we will use a few methods. Okay, we'll look into it. So basically what is it? When the radar is a moving platform such as ships, aircraft and spacecraft, the Doppler frequency shift from clutter is no longer zero frequency. So the Doppler frequency of the clutter echo depends on the relative velocity with respect to the moving radar platform. So it will vary with the speed of the radar platform as well as with the angle and elevation of the clutter cell with respect to the radar. So basically it will the position of the radar and pointing, all this will affect the clutter. Okay, the change in clutter Doppler frequency by changing the frequency of the coherent uh, coherent or reference oscillator in an open loop manner. If the speed of the platform and the direction of an antenna pointing are known, we can do this. Okay, so basically you can change the clutter Doppler frequency by changing the coherent reference oscillator. And here we need to have to be know the direction of the antenna and pointing which point and the speed. Okay, and so when we know that, we can change the Doppler clutter Doppler frequency. Next, compensation for the clutter Doppler frequency can be achieved by mixing the output of the coherent with a signal from a tunable oscillator whose frequency is made equal to the clutter Doppler. So basically we will use a tunable oscillator here which matches with the clutter Doppler. Okay, uh, that is one method. And here coming to airborne moving target indicator has to solve two problems due to clutter. One is change in the center frequency of the clutter. Okay, basically clutter Doppler fixed will tell. So basically how it will be when I try to draw this, one will might occur here. Let us take this is a clutter. It's not will be in it is not in the equal intervals. It might shift, like for example if it shift like in this, and it might go from here to here and here, like somewhere like a shift. Okay, it will be not a constant, right? And next, widening, increasing the cluster spectrum width more than the two clutter falling within a single resolution cell. Next, so increment in the cluster spectrum width basically. So this width will be increased. Okay, if it is in the previous case, it might be like this. Okay, now it is got increased. See, that's what. And the widening of the cluster spectrum is due to the finite beamwidth of the antenna, which makes the Doppler frequency shift from the cluster pattern within the radar resolution cell resolution cell differ depending on the location within the antenna beam. So basically the reason for widening of cluster spectrum is due to the finite bandwidth, beam width, finite beam width of the antenna. Beam width, you know, right? So beam width is like, for example, if it is a radiation pattern, if this is the radiation pattern, so for this the beam width might be theta b. Okay, how it's separated? There are like two, basically it will be like one more thing, it we call it a half power beam width. From that we can, so we can also call it as half power beam width also. First problem is basically we can generally in a layman terms we can say how wide it is, the beam. Okay, the first power is solved using TS. The first problem is solved using TACCAR, that is time average clutter coherent airborne radar. That means we can solve this, okay, using TACCAR. Okay. Right. Okay, TACCAR means time averaged clutter coherent airborne radar. Second problem is solved using DPCA. DPCA means displaced phase center antenna. Okay, so compensation for clutter Doppler shift. That is the first case, right? To resolve this first problem, we are using this TACCA, time average clutter coherent airborne radar. So for this, the the TACCA, how it works, let's see. So the Doppler frequency shift from clutter can be compensated by using the clutter echo signal. One can use clutter echo signal frequency to set the frequency of the reference oscillator or coherent, so that the basically reference oscillator and the coherent oscillator are the same. So we'll call coherent oscillator as coho, right? So that the rejection of the MTI Doppler filter alters the clutter echo. So if you know that echo frequency or the clutter echo signal frequency, just by matching the oscillator, the reference oscillator or the coherent oscillator to that frequency, to that echo signal frequency, then we can filter it out. Okay, so that what happens, it will reject the MTI Doppler filter alters the clutter echo. So this MTI, we know we have used MTI Doppler filters, a Doppler filter. So basically these Doppler filters we can alter this clutter echoes, moving clutter echoes. So clutter echoes, a similar problem occurs in a stationary radar when the clutter has a velocity of its own. So basically this can be occurred in the other way also, when the clutters are moving. Okay, when these clutters are moving also, we'll have the same issue. The similar problem occurs in the stationary radar when the clutter has a velocity of its own, as might occur for ocean currents, weather and wind blowing larges. Basically what happens, even I told you an example of a man where the man is standing on a boat, even due to his heart, like heart pumping. So due to the motion of the heart, the radar detects that human is moving, but he is not moving. So that is a clutter actually. So that moving of heart is a clutter, but still the station. Now what happens is standing on a boat. So due to winds or weather current, motion currents, the boat is also moving. So both the clutter is itself moving. Okay, yes, right. This is a clutter. The heart is a clutter. The clutter is now moving on the boat. So that's what, in that situation also this will happen. So compensation for clutter Doppler spread. Clutter Doppler spread means the widening of the clutter this width. Okay, that can be done by DPCA. So Doppler displaced phase center antenna. So how can it do? Basically there will be, for example, let us take this airborne antenna, and this is radar and moving platform moving at a velocity v, and there is stationary clutter here. Then let us take a tree, and when you are moving this so basically in the direction of the tree, what is the velocity of the airplane is Vr. That Vr is v cos theta, right? So the Doppler frequency shift of the echo from the stationary clutter when viewed by the moving radar is given by. So what is the Doppler frequency shift of the echo? So Fc is equals to, basically we call that Doppler shift for a stationary clutter when received by a moving radar is Fc. Okay. That FC is basically, previously we called it as FD. The same thing we are calling it as in general we have FD is equals to VR by lambda. That same thing, that FD is replaced with FC. That's it. 2 lambda by VR. VR is V cos theta. So 2 by lambda into cos theta. V is the velocity of the platform carrying the radar. Lambda is the wavelength. Theta is the angle between the velocity vector of the vehicle carrying the radar and the line sight of clutter scatter. This is the angle basically he's telling about. Now the Doppler frequency from those scatters located along the center of the antenna beam will be compensated by TACCAR so that it appears at zero frequency. So what happens is Doppler frequency from those scattered locations along the center of the antenna beam will be compensated by TACCAR so that it appears to be zero frequency. So basically we are not yet done. Basically if we do the TACCAR, so basically this TACCAR we have done previously, right? So by using that we can this Doppler frequency scatter we can locate like we can compensate the TAC what I'm saying, sorry. Locating along the center of the antenna beam will be compensated by TACCAR so that it appears at zero frequency. So basically this what we will do is we make sure that when this pulse repetition frequency occurs, like for example this is the pulse repetition frequency like this, and these are the FPs and all. So if there is we make sure that it is staying in this zero at this point. Okay, we make sure this clutter echoes are occurred at this zero by using TACCAR. Basically if we are not using TACCAR, what happens, they might shift to some other places like here or some here or somewhere here like that. So we are making using the TACCAR, making that present in this zero frequencies. See that so what happened, geometry of a scattering of a single scatter location of an angle alpha for the beam center antenna beam width is equal to 0. So this is a radar and this is a clutter scatter. We are sending a beam that has oh nice. So this is the beam center. Okay, now what happened, this antenna had a beam width of so basically this is the beam width theta b, and this is a clutter scatter. It is not along with the center, it is somewhere outside, off by an angle alpha. Okay, this center makes an angle with the flight path theta. Okay, here the echoes from all other scatters that are not lie on the center of the main beam will not be compensated by TACCAR. That means if this line is along this beam center, then it can be compensated. He's saying that the echoes for all other scatters that do not lie on the center of the main beam will not be compensated by TACCAR. Thus, there will be a spread in the clutter Doppler frequency spectrum due to the finite antenna beam width. So what happens, there will be a spread in the clutter Doppler frequency because they are not lying along the beam center. So the clutter spread due to the many clutter scatters within the finite beam width can be found by taking the differential to the Doppler frequency. So Fc is equal to V lambda by cos theta, right? We'll differentiate this Fc with respect to theta, and then we found out, and we actually there will be cos theta, right? When you differentiate minus sin theta, with this minus will be neglected. So dfc is equal delta fc is equal to v by lambda d, and this delta theta can be written as d theta b beam width to sin theta. Okay, and so the same thing. So width of the, so this is the width, delta fc is the width of the spectrum. So when theta is equal to 0, antenna pointing along the flight direction, right? The theta is what in this diagram. Here. In this diagram, this is the theta. If this theta becomes 0, that means along the flight path, we'll what we'll get FC is the maximum. So theta is 0, 1, right? So you'll get delta FC is the spread in minimum. So spread is minimum. So when theta is equal to when theta is equal to 0, the entire term will become 0, right? So there is the change delta f to the width. So the width becomes 0. That means it is the minimum, right? That is 0. That is what the spread will be minimum. That is 0. Okay. And when theta is equal to 90, broadside, that is perpendicular to the direction of the path or direction of the vehicle going. So when theta is equal to 90, FC is 0 because the sin theta will become 1, and this term is so basically what he is saying, FC means use the formula of cos theta, okay, as this formula. When 90 is 90, that means cos 90, right? Cos 90 is 0, that is FC is minimum. Then wait, where is this? So the FC becomes 0 basically. So FC becomes 0, that then delta FC is maximum because this is 1, right? So that's what. So at 90 means like this, the beam is like this. So we can see here two cases: change in shape and location of cluster spectrum due to platform motion as a function of azimuth. Okay. So when you have used here the case for a very high PRF or continuous CW is a continuous. So when you use high frequency PRF or if you use continuous wave, the first case will happen. That means it will be shifted to different locations. Okay. For one, when theta is equal to 60, it will be looking like this. When theta is equal to 30, it will be here, and width is also changed. When it is at 0, it will be like with the 0 width as we seen above. Okay, and at theta is equal to 0, what happens? The DC is 0, right? Delta FC, that's what here we saw. Okay, so now in the second case, when theta is equal to 90, okay, when spectrum folded about the PRF at 360 Hz. In this case, what happens at 90 degrees, we'll get the maximum width, right? So see how much this is a cluster width, how wide it is. So you can observe, right? So that's what, and it's centered at 360 Hz. And 360 Hz is the pulse repetition point, where frequency of pulse repetition. So and wait, and then these are the problems. They will be direct only. You can directly find using the formulas in the above question, above classes. Yeah. So there will be no spreading of the cluster spectrum when delta FC is 0. That is what we saw previously, right? So when we'll get the delta FC is 0, when theta is equal to 0, right? So when theta is equal to 0. So if the antenna would be made to think that it is stationary, it is possible to do this with these two spectrum antennas. That means what is happening in the previous was, as the antenna is moving, the angle theta is varying. That's why it is. That's why this is happening. So if we made the antenna such a way that even it is moving, the theta. So even it is moving. If you don't, what you call? Sorry. Even if the antenna is moving in real world, if we made to think that antenna is not moving, okay, then we will get this condition. So we can make it by, it is possible with the two separate antennas. So how to make is, in a plane at the front we will keep one antenna, at the end we will keep an antenna. What happens? It will transmit and send, right? When this is moving, basically these are separated by spacing. The spacing value is V into TP. V is this velocity of this platform, and TP is the basically pulse repetition period. Okay, so when it sends the data here and it come back, right? This is stationary clutter. When it is moving, okay, and it will reach this point, okay, and then it will again send. So again it will detect the same object. That means even it is moving, it is send. You understand, right? So but the computer don't know, right? So it is sensing the same object twice. That means it feels that it is not moving. Okay, so that's what. So the first pulse, so that's what he's saying. So this is the method. Actually the first pulse is transmitted and received by the forward antenna. Okay, it will send and receive. When the trailing antenna arrives at the spot when the forward antenna was, when it transmitted its pulse, that means when it transmitted the same spot, this is the spot, right? This is the spot. And when the trailing antenna also came here and transmit and receive the same spot, at the same spot. So if there is a so as it's there is a single stationary antenna. So the two pulses are then processed in a delay time canceller, and there is no effect of platform motion. So this is what we used actually previously, delay line canceller. We have used delay line canceller, and so single delay line, a double, triple, like that, no? That's what. Now coming to DPCA, that is displaced phase center antenna. So consider a mechanically rotating antenna that generates two. Basically what it should do, DPCA should decrease the width of the coherent, right? So this, let us do this. So consider a mechanically so that's already we have done that, right? Using that formula we saw that 2v by lambda into sine theta, or 2v by lambda into cos theta. We found that that is the fc. From that we found delta fc, and also we'll just study more in this displaced phase coherent antenna. Consider a mechanically rotating antenna that generates two overlapping squeezed beams. So squinted and means basically this is the squinted beam. So two beams will be generated. One, the sum and the difference delta of the two squinted beams taken. So one will take the sum of these two, means another inside the process is like beam A and beam B. One will take the beam A plus beam B, and other will take beam A minus beam B. The sum beam is used for transmit, and both the sum and the difference beams are used on receiver. Okay. So while transmitting it will only use the sum port, but while receiving some basically it will take the sum only, sum of the two beams while transmitting. But while receiving it will take the difference and sum of both the beams. So beam A, beam B. While transmitting it will only check for beam A plus beam B. But while receiving it will check for beam A plus beam B and beam A minus beam B, like that. So phasor diagram illustrates the nature of DPCA action of compensating for platform motion using the sum and difference patterns of two squinted beams formed by a single antenna. Okay. Phasor representing the clutter echoes signals received on two successive pulse transmission. Phasor, this is the phasor representing two pulses, and the angle between them are 2 eta, represents the phase change due to the travel. So this is due to travel. When basically if it is like this and it is sending, and again it is moving, right? So what happens when it moves? So actually previously it is like this. Okay, this is the beam wave we are telling, and when it moves it will be shifted towards somewhat side, right? That shifted is the thick line. Okay, that's what these two beams, that's what they are telling. One will be the old one, that one only when it is moving it got shifted to some little bit distance to this. So due to this travel, let us think that it is like it is previously it is like this, and it is mainly due to moving it is gone like this with the angle of separation 2 eta. So this is the correcting. This is for corrections applied to each pulse, so that a cancellation of the clutter echoes occurs on two successive pulses. So we are taking the resultant of this and like that. Okay, we are taking E1 as this one after correction. This is E1 as this one and E2 as this one. So now what is the pulse Doppler radar? So equation derived in second section for nth blind speed, right? We have seen the speed, the formula for nth blind speed, that is Vn is equals to n lambda by 2 Tp. Okay, where n is equal to 1, 2, 3, 4, 5. So Doppler, here this is one first equation. No, Doppler space, the Doppler region where desired moving target can be detected. Okay, the Doppler region where the desired moving target can be detected. A reduction in the available Doppler space causes loss in the detection of moving target. Yes, no. For example, uh, in this, if for example this is the region where we can detect the target, and basically this is the reason we need. Basically, this is the reason we need to detect a target. But what happens? This region got decreased now. So now the region, or we'll see with the red color. So now the region got decreased. So basically the chances of detecting the target got also decreased, right? So that's what he's saying. The reduction in the available Doppler space causes loss in the detection of moving targets. Uh, mm. So the degradation of performance caused by the blind speeds can be especially difficult in airborne radar, which operates at high frequency in order to have small antenna on moving platform. So in addition, airborne radars suffer a widening of cluster spectrum wide due to platform motion, and thus further aggregating the reduction in the Doppler space available for detection of targets. So as we already seen, one problem is like due to blind spot can also be occurred in these airborne radars due to they are using high frequencies. Okay, and also in addition to airborne radar suffers a widening, right? That cluster will be widened. I, yes, no, do you like this? Like this, the cluster might be widened. So pattern motion, and thus further aggregating the reduction in the Doppler space available for detection of target. That means if this clutter space increases, what happens in that region we can't detect a target, right? So these are all the properties that where we can't, which are affecting the detection of moving targets. And according to the equation, increasing the PRF increases the first blind speed and reduces the number of nulls found within the Doppler space. Okay. According to equation 1, increasing the PRF increases the first blind speed and reduces the number of nulls found in the beam. Okay. So let us take this is the that is 0 to 2 fp is the desired Doppler space. For example, here we got one blind spot, right? But high PRF increases the problem of range ambiguities. Uh, mm. So basically, what he is saying is, if you increase the PRF, this blind spot is there, no, the nulls. Basically, these are also nulls. So these will be reduced. But if we use high PRF, what happens? The problem of range ambiguities also will come. Ambiguous lines like that. So ambiguous range, you understand it. We think that the target is it's like for us the target will be looking at some 5 kilometers, but actually it is at 10 kilometers like that. So therefore that trading of both Doppler ambiguity for range ambiguity in somewhat that we need to rate in order to obtain good detection of moving targets at the high operating frequencies. Since the radars will operate at high frequencies, we need to have a trade-off between both Doppler ambiguity and the range ambiguity. A radar that increases its PRF high enough to avoid the problem of blind speeds is called pulse Doppler radar. So when we are using PRF of high frequency high enough, so that to avoid this problem of blind speeds, then this radar is called pulse Doppler radar. At high PRF, pulse Doppler radar is one with blind speeds within the Doppler space. at high PRF, pulse Doppler radar. Pulse Doppler radar is one which no blind spots within the Doppler space. So when you use pulse Doppler radar, we won't get any blind speeds within the Doppler range or Doppler space. So that the three different types of pulse Doppler radars. One is the MTI, moving target indicator, with no range ambiguity and many Doppler ambiguities. When this condition occurs is when you use low PRF. So these are very important. And then the high PRF, pulse Doppler with many range ambiguities and no Doppler ambiguities. So when you use high PRF, what happens? There will be no pulse Doppler with many range ambiguities will come, but no Doppler ambiguities, because we are not getting any of this what you call blind speeds when you use high PRF. A high PRF pulse Doppler radar is one. Okay, sorry. The medium PRF medium PRF pulse Doppler radar, both ambiguities will come, but to some extent only. Okay, when you use medium PRF. So what is the high PRF pulse Doppler radar? We'll see this here in the next video.